So there are different types of chemical reactions that we can talk about, and it actually matters on where the reaction it is taking place, and it is taking place under what conditions, because the conditions that are surrounding that chemical reactions, they play a major role in that chemical reaction. The conditions, we will be looking at the temperature around that chemical reaction. We will be looking at the pressure, right? We will be looking at the volume at which that reaction it is taking place. And then again, even the nature of the substances that are reacting with one another, we'll be looking at that. And on top of that, it's very important to understand whether the reaction it is taking place in a closed system or it is taking place in an open system. Because for a reaction to reach equilibrium, it must be happening in a closed system. So now this is what is happening. When we reach the equilibrium, that means the rate of the forward reaction, it is equals to the rate of the reverse reaction. Remember, you and I, we did the rate of reactions, right? But the rate of the forward reaction is equals to the rate of reverse reaction when we reach the chemical equilibrium. Do you understand that? So now, when the equilibrium is reached, there are disturbances that are going to take place. For an example, this is you, Lina. You are in the laboratory. You are running your chemical reaction. In the chemical reaction, it is happening in a closed system. And then you decide to increase the concentration of your reactants. You're like, okay, you know what? The reactants, now I want to increase them. Let's say your chemical reaction, it has already established the equilibrium. The moment you increase or the moment you introduce the reactants, you're going to disturb that chemical reaction that is at equilibrium. And then the nature of that reaction will try to counteract that change that you have introduced in the chemical reaction. That's where the Chatelet principle comes in, that when a chemical reaction it is at equilibrium, the chemical reaction itself will try to re-establish a new equilibrium, okay, by favoring the side that produces more. You will see that, right? So that's what is happening in a nutshell. But obviously, there are calculations that are involved, such as the equilibrium constant, which is called Kc value. We'll see on how to calculate all of those things. Do you understand what I'm saying, Lina?
Yes, I understand.
Okay, so let's start. Now, start with the basics step by step, right? So this is the definition of what is equilibrium before we can talk about the chemical equilibrium. At equilibrium, it is where we observe no change as time goes by. Remember, chemical reaction will start, right, in a vessel. It will start whereby the reactants will interact with one another. And then the products are going to be formed at a certain rate, right? As the products are formed, there is a time whereby now the products will form the reactants back. Meaning you form the product at first, the product because there are no products, right, in a vessel. So there are no products at all. You only have the reactants. Time is zero. The moment you start hitting that stopwatch, what's gonna happen? The reactants, they're gonna come together and interact with one another to form the products. Now we're gonna have a certain concentration of products in a vessel, right? So now those products are going to be continuously formed until there is a time whereby those products they're gonna react back to one another and form the reactants back. The moment the product starts to form the reactants as time goes by, in terms of the rate of reaction, when the reactants form the products and when the products form the reactants at a constant rate, then we reach what we call the equilibrium. But in this sense, because we are talking about the chemical reactions and we have already spoke about the rates of reactions, then we are talking about the chemical equilibrium. And so, I having a look at this definition over here, it says to us chemical equilibrium is achieved when the rates of the forward and reverse reaction are equal, and the concentration of reactants and products remain constant. Like I said to you, the reactants will form the products will form the reactants back at the same rate. Meaning, when the rate is the same, there will be no more increase in a concentration of the products or decrease of the concentration of the reactants. Okay, that's chemical equilibrium. Now, there are two types of equilibrium. We have the physical and the chemical equilibrium. The physical one, it is the one whereby your reactants do not break into different atoms. For example, we have water from liquid to gas. Liquid, gas, it is H2O, right? So that's a physical equilibrium. When water forms a gas and a gas forms water back, that's a physical equilibrium. But when we have uh, again, when we have kind of reactions like this, dihydrogen tetraoxide, like this one over here, we can see that N2O4 will form now a total different product. N2O4 will form NO2. You see, that's a chemical. So basically, chemical is when we break it down into smaller pieces and then we form different products. Meaning, I mean different products in terms of their molecular structure. So in this case, we can see that N2O4, it is now turned into NO2. So this type of equilibrium, it is called the chemical equilibrium. But water in liquid forming gas, which is still H2O, that's a physical equilibrium. Okay, all right. Now, what do you see over here? It is a beautiful jar that has a beaker inside of it. Inside of that beaker, there is a chemical reaction that is taking place, which is a physical equilibrium. Water will condense, water will evaporate to form gas, and that gas will collect and then condense to form water back. And have a look at this. This is a closed system. There's nothing that is escaping out of this chemical reaction. So that's why we say it is equilibrium, because I'm saying to you, equilibrium, it takes place in a closed system. And then this is a chemical equilibrium. So now in this case, we have a chemical equilibrium inside of a closed, this is a glass, I can't remember what they call this thing, but the chemical reaction is taking place inside of it, right? So it is sealed, it is closed. There is no matter that is escaping out of this system. But you have to understand that the reactants, they're going to form a total different molecular structure of the products, like how I showed you at the beginning. So meaning in this case, we are having chemical equilibrium. Now, this is the equation that we spoke about when we were talking about the chemical equilibrium, right? This is an example of a chemical equilibrium, of which this is what we're going to do. We're not going to do physical equilibrium, we're going to do chemical equilibrium, okay? So it was just to distinguish to you what is a physical and a chemical equilibrium. So in this case, we have the sketches of our reaction over here. So we have figure A, on the y-axis, we have concentration, and on the x-axis, we have time. This, it is a reactant. Let's go locate it on the graph. This, it is a reactant. What do you realize? This is what is happening. In this case, okay, this is a reverse reaction. When you have a certain product, so meaning when the reactants are being used up, what is this thing? When the products are interacting with one another, meaning the concentration of the products are decreasing. Therefore, we can see that now the reactants are being formed. Same applies to here. We start with a certain concentration of our reactant in a vessel, right? Maybe whatever concentration, mole per cubic decimeter, and then here's going to be zero, obvious, because it is a product. We are about to form a product, right? So now, when the reactants react with one another, their concentration obviously it will decrease because we are making use of those reactants. So with the concentration of the reactants will decrease while simultaneously the concentration of products increases because we are forming the products until there is a time whereby equilibrium it will be reached. Now having a look at this linear flat surface here of our functions, this is where the equilibrium it has been established. So for an equilibrium to be established, the reactants must be used up and the products must be formed. So how do you see that the reactants are being used up? The concentration decreases because we are making use of them. So initially, the concentration of the product is zero. That is why we start here at the origin for NO2, N2, NO2, because we know that NO2, it is our product. We are about to form it. So hence why initially we have zero, but for N2O4 we have something because it is a reactant that is inside of the vessel. You get my point. And then simultaneously, this and this, they will move at the same time, obvious. The reactants are being used up while the products are being formed, right? And then there will be establishment of an equilibrium. Now here, when the equilibrium it is reached, there will be a disturbance. Now we are jumping to diagram C. There will be a disturbance. The disturbance is what? Look at this. So the disturbance is we have increased the concentration of N2. When we increase the concentration of N2, remember this is equilibrium number one. So when we increase the concentration of N2, therefore the product will interact alone. The product will, you will see, we'll learn that in more detail. The product will react in a certain way, I mean the product will decrease further, and when decreases further, and then now another equilibrium will be reached. So this is the second equilibrium. So in chemical equilibrium, this is what you need to understand, Lina, in a nutshell, not to confuse you. In a chemical equilibrium, you should know that a reaction can reach equilibrium and you can disturb that equilibrium. When you disturb that equilibrium, the chemical reaction by itself will try to re-establish a new equilibrium. But that new equilibrium will most definitely be different from the first one. Do you understand? It is the same as you right now, you are studying, right? And then maybe your cousin comes with a loudspeaker while you're busy studying. What are you going to do? You're going to interact with your cousin. You'll be like, no, man, stop playing that. You're disturbing me. Meaning you counteracting there what the disturbance. And then what are you going to do? You're going to reach a new equilibrium again to continue studying with your work. That's how chemical reaction actually works. Do you understand how does the chemical reaction, chemical equilibrium work in terms of disturbances and whatnot?
Yes, sir.
Okay. Awesome. Now, let's talk about law of mass action. Now, when you talk about law of mass action, we say that for a reversible reaction at equilibrium and constant temperature, a certain ratio of reactant and product concentration has a constant value K. Okay, so now this is where we have at equilibrium. I showed you that this is what we call equilibrium here. We have here we have established what's happening now? We have established the equilibrium. Ne? At equilibrium, that's where we're gonna have law of mass action. That for a reversible reaction, remember there is a forward reaction. Reversible reaction is whereby the reactants they're going to interact with one another. Right, so we must make sure that we have a constant at the constant temp and the constant temperature. So the certain ratio of reactants and products concentration has a constant value, meaning we're going to have the constant value throughout for concentration of the reactants as well as the concentration of the products. So the equilibrium constant, which it is enhanced or influenced by law of mass action, we say the equilibrium constant, it is a number equal to the ratio of equilibrium concentration of the products to the equilibrium concentrations of reactants, each raised to the power of its stoichiometric coefficients. Let me tell you in a simpler way how to understand this. So we say the equilibrium constant, it is called Kc. Ne? The Kc is equals to the ratio of the concentration of the products divided by the concentration of the reactants. But this is not how we express it. I just want you will see there is a way on how we express it. Ne? So if you have a chemical reaction like this, A, B, these are the stoichiometric coefficient B, CC, and D, capital letter D. So assume that this is a chemical reaction, right? On the left-hand side of your reactants, on the right-hand side of your products. So to write the expression for equilibrium constant, you're going to say Kc is equals to the concentration of the products at the top. So in this case, C, it is a product. And then this stoichiometric coefficient, you raise them over here as the exponent. And then for D, and then stoichiometric coefficient, we raise it over there, divide by the concentration of the reactants. Our reactant is A and B, so we say the concentration of A and the stoichiometric coefficient is going to be A, and the concentration of B and then the stoichiometric coefficient is B, and then this is how we express the the equilibrium constant of a chemical reaction. That's what they mean here in words. Okay, all right. Meaning at equilibrium, this is what is happening. Kc, we have Kc here at equilibrium. Here. It's either this equilibrium or that equilibrium. We have Kc value, and this is how we simply calculate the Kc value. Okay? And just like how I showed you, you see? Yeah, CDAB. Yeah, and then this is how I showed you, right? Like if you have a chemical reaction like so, you can express your Kc value like so. Okay? All right. So now, let's have a look at this chemical reaction. N2O4 in a gaseous state, forming 2NO2 also in a gaseous state. In this case, we have a constant temperature of 25 degrees Celsius. So, Lina, focus, ne?
Yeah.
Here we're going to talk about the initial concentrations. The initial concentration of NO2. What is NO2? NO2 is a product. So initially, you do not have a product because the reactants, they haven't started to react. How can you have a product without reacting, the reactants reacting? The reactants should react first so that you can have a product. So obvious, initially, the concentration of the product is zero. But because this is a reactant, there is initial concentration because this is you in the lab. You know, okay, I'm going to put this concentration of N2O4 in the vessel. You know its concentration. It is a known concentration initially. As time goes by, the concentration of your reactant, which is N2O4, which is 0.670, that concentration will decrease. Why the concentration decreases? Because the reactant, why the concentration of the reactant decreases? Because the reactant is being used up. The reactant is being used up to form a product. So meaning the moment 0.670 of your reactant drops, Therefore, there will be raise or there will be rise. There will be rise in the concentration of the product. There will be something that will be formed for the product. The moment times moves, I get, but at time 0 second, therefore product is 0, reactant is 0.670. Now, time goes by, the reactants are being used up, the products are being formed. Now, the concentration of the product starts to increase, starts to increase, starts to increase. You understand? And then there is a time where we're going to reach the equilibrium. Now, the concentration of the product and the concentration of the reactant, it is now stable. It is no longer changing. Now we have reached the equilibrium. What does that mean? That means the way the reactant is forming a product, the rate at which the reactant is forming a product, it is the same as the way of the products are trying to form back the reactants. So the concentration will never change at all. The concentration will remain at this point over here. But if you disturb this equilibrium, obvious, the concentrations, they will change, but you will see how. So if we are talking about the ratio of concentration at equilibrium, you're going to take your calculator, you're going to say the concentration of this guy divide by concentration of this guy. Now we are looking for Kc. The ratio of concentration at equilibrium, that's the Kc value. That's how we calculate the Kc. I told you that you're going to say the concentration of this. And by the way, account for your stoichiometric coefficient. Here, stoichiometric coefficient, it is 2. And in here, your stoichiometric coefficient, it is 1. So that means definitely you will be saying 0.0547, right? That's a product, right? Divide by 0.643. And then you will get it over there. You will get your 0.0851. Understand? Okay, that's the ratio of
Yes,
concentration
sir.
to the plant. But when you want the Kc, you account for your stoichiometric coefficient. When you put your squared, because here it is 2, here it is 1, so that's why here we have to the power of 1. Obviously, it is invisible. It's not necessary for them to show that there is 1 there, but 2, obviously, we have to show there is 2 here from the balanced equation. Then you will get this number over here. That's Kc. You understand?
Yes, sir, I understand. I got it.
Okay. Sometimes you can put a reactant in a vessel that has a product already with a certain concentration. It is not always the case that you put your reactant where there is no product. It is the same as you saying you have water, right? You have liquid in water, water in liquid, and you put ice inside of water, and you want that ice to melt. Obvious. Here's the thing: there are two scenarios. You can put ice in a jar where there is no liquid. Obviously, we want to form liquid. Therefore, the concentration of liquid is going to be 0, but the concentration of ice is going to be something. Or you can put ice inside of the liquid. Already we have a product. So when you are adding the reactant to a product, because we want to take that ice into a liquid, but you are adding ice inside of a liquid. So in that case, that's where now we have a product and a reactant initially with a certain amount. So that's what we are looking at over here. But most of the time, where initially you have a concentration, it's when you disturb an equilibrium. But you will see, okay? It's fine. You will see. Don't stress. You will see. Like I told you that I check something. Um, okay. So now we have the chemical, we say the chemical equilibrium is defined by K, sharp fine. The magnitude of K will tell us, okay, now the magnitude of K will tell us if the equilibrium reaction favors the reactant or the product. Okay, I'll explain to you what does the favors mean. You know what does the favors mean? The favors mean we have more products, then we will favor the product side, which is the forward reaction. Or we have more reactants, then the reaction will favor the reverse reaction where we have more reactants. So if Kc it is greater than 1, it will make sense to you why I'm saying that. Recall that at the top we must have the concentration of the product, at the bottom we must have the concentration of the reactants. So if Kc it is greater than 1, let's assume that I'm just making an example. So we will make P to be more, and then we'll make R to be less, concentration of the reactants to be less. Let's say here for product, we'll say we have 10. I'm just making an example, okay? For product, we'll make product to be more than the reactants. The product are more, we have 10, and in reactants, let's say we have 5. So 10 divided by 5, it will give us how much? It will give us 2. This value, it is greater than 1, right? So when the Kc it is greater than 1, it means we favor the product. Why? Look, mathematics. Chemistry means maths. According to maths, we know that the value at the top, it is directly proportional to our variable on the side of the equation. So meaning the higher the products, we're going to have high Kc value. But if we have more reactants than the product, let's say the product now it is 5, the reactant it is now 10. What is 5 divided by 10? It's going to be 0.5. And a 0.5, it is a value that is less than 1. You know why? Because we have more reactants. So if we have more reactants, therefore the Kc value will be less than 1. If we have more products, the Kc value will be greater than 1. In this case, whereby the Kc value it is greater than 1, if the forward reaction, it is where we forming the products, then the forward reaction will be favored. We favor the side that produces more. I'm saying to you, we favor a side that produces more quantity. When the Kc is greater than 1, that means we have more products. Therefore, we'll favor the product side, or you can say we'll favor the forward reaction. But when the Kc value it is less than 1, that means we have more reactants. Therefore, we will favor the reactant side, or you can say we will favor the reverse reaction. Ne? Okay. Here's the thing. Ne? We're not going to talk about the KP. For your curriculum, KP is not assessed. Pressure of gaseous, what, this is not assessed. When are you only looking at the Kc? So I'm going to hold it back here. And then what I want us to talk about is the factors that affect chemical equilibrium, okay? I see here on these notes, I want to check if those factors are here. This is varsity stuff. When you don't do this. I'll show you something. Yeah. Okay. Something that I want to show you, né? Yeah, this one you will do it when you get to the university. It's not for you this part. I just put this material from somewhere. Okay, I want to explain something to you. Okay, this is what I want to come. Then we're gonna look at the factors that affect chemical equilibrium. There are 4 factors that affect chemical equilibrium, and I heard that you spoke about the catalyst. The catalyst, yes, you were correct. The catalyst only affects the rate of reaction, just like how we did it under the rate of reaction. We said about 6 or 7. factors that affect rate of reaction. But here, yes, we still talk about the rate of reaction under a chemical equilibrium, but we want the factors that affect chemical equilibrium alone. There are four of them. It's the concentration, the pressure, the volume, and the temperature. The catalyst, they love asking that question. The catalyst does not affect the chemical equilibrium. The catalyst, it only affects the rate of reaction, not the chemical equilibrium. And that's what you said. I love the fact that you said the rate of reaction. I was like, oh, okay, that's good. But I was happy that you did not say it affects the equilibrium. Ne? It does not. So now, here's the thing. Why do we say these are the factors that affect chemical equilibrium? Remember, I said to you, when the reaction reaches equilibrium, there will be a disturbance. So what will be that disturbance? How do we introduce a disturbance? These are four factors that are gonna disturb that chemical. If you change the concentration of the products, or if you change the concentration of the reactants, you're gonna disturb equilibrium. If you change the pressure in the vessel, you're gonna affect the equilibrium. Just like you will see this more especially when you go to university working inside of the distillations. If you want to change the outcomes, the product, you have to change the pressure. You understand? If you change the pressure, you are changing the equilibrium. If you change the volume, you are changing the equilibrium. If you change the temperature, you are changing the equilibrium. You understand? You are affecting the equilibrium. That's how we disturb equilibrium. And then after we disturb equilibrium, how can we counteract that? That's where Le Chatelier comes in. And then Le Chatelier's principle says that if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset as the system reaches a new equilibrium position, just like how I told you. These are the factors that affect chemical equilibrium. This is chemical reaction minding its own business at its equilibrium, undisturbed, unprovoked. And then Linamandla, as a chemical engineer, comes along, change the concentration of the reactant. Reactant will be upset. The reaction will be upset at you, Lina, because you are disturbing its process. It is at equilibrium, it is chilled, it is there in the ocean, coastline, enjoying nice music, drinking tropical juice. And then when you come there and, mess up things by adding concentration of the reactant. And then you know what chemical reaction will do? Will say, okay, Lina Mandla, you are disturbing my process. Le Chatelier realized something. This great person realized that, or if you disturb that chemical reaction that is at equilibrium, that reaction itself, it will find a way to counteract that change that you have introduced. And that change or that factor that you have introduced in a chemical, a new equilibrium will be established. Therefore, it will settle at that new equilibrium again. Then you come back again, you disturb it, you disturb that chemical equilibrium. You know what's going to happen? It will still reach a new equilibrium. Whatever you do, you will never break it. So that's how it goes about. Changes in concentration. We will talk about this later on. But for now, I want to ask you